Hello, my name is Isaac, but I'm not Newton, and I'm not even trying to be one. But at the same time, I'm not trying to rubbish your knowledge of Newton's second law of motion, and I'm not trying to delete whatever you have learned in your high school about Newton's law of motion. In fact, what I'm here to do is to make you have a better understanding of what this law states, because I perceive that a lot of people perceive the law in a very wrong manner. So what I'm going to be doing in this video exactly is to let you know what the law says, what are the agents, what are the elements that the law comprises of. Now, so I'll start by stating the law. So we know that Newton's second law of motion states that um, according to Wikipedia, so I'll be using Wikipedia as my reference here. So according to Wikipedia, Newton's law of motion, the second one, says that a body that is acted upon by a force moves in such a manner that the time rate of change in momentum of the body is equal to this force. So with that, that implies that according to this law, we have a body. There's a body. Of course, if you have a body in physics, that implies that the body will have a mass m. So for the body, we have mass m, and there's a force say F. So these are the two things that we'll be focusing on here. So there's a force and there's a body which have mass m. So this force acts on this body and it causes something on. But before I go further, what is force really? Force, I know many people will say that force is the product of mass and acceleration. Well, fine, that is an expression. But really, to define force, we can define force as this. Force is an agent that tends to cause a body at rest to start moving. So it is an agent that tends to want to make an object that is at rest to start moving, or an agent that tends to change the course of motion of a body that is already moving. So that is, if a body is already moving uniformly in a straight line, if you apply a force on that body, then the body changes the way it moves. Or if the body was not moving before, the body was at rest, what happens is that if you apply a force, the body is expected to move. So this is what force is. Now, this is giving us an insight that whenever force is applied, movement is actually supposed to occur. So, and from the equation that is the bone of contention in this video, from F equals to ma, let's do some little mathematics here. Now, we know that for a body will definitely possess mass, which means that m can never be equal to 0. M can never be equal to 0. And since m can never be equal to 0, this equation will hold. For if f is going to be equal to 0, it implies that a itself has to be 0. And the reverse is also true. At least a equals to 0 implies that f equals to 0. Now, which implies that 0 cannot, none of this can be 0. F cannot be 0 without a being 0. A cannot be 0 without f being 0. Now, the question is that since we know that the body can never have a 0 mass, and you have applied a force on an object, then that implies that acceleration is not supposed to be 0, which means that there ought to be movement. Whenever there is acceleration, movement is meant to occur. So what we're saying is that if a baby, I'm talking about a baby that is wise enough to be able to push or pull something to himself or herself, if a baby should apply a force on a very heavy object that is resting on the floor and the object does not move, the reason the object is not moving is not because the baby does not have enough force to be able to push or pull this object. There's a reason why this object will not move, and the reason is not because the applied force is not enough. In fact, just from what we have seen here, we can see clearly that it is impossible for you to have a non-zero force and have a 0 acceleration. Based on this equation, actually, So, which implies that this equation is already having problem from here. A non-zero force should not produce a zero acceleration. And because the object did not move, that means that there has been no acceleration. There are two cases whereby acceleration will be equal to zero. When an object is not moving at all, or when an object is moving with uniform velocity. These two cases, there will be zero acceleration. So the maybe applied force on the object that is on the floor, a very heavy object, and the object did not move. That implies that the body did not accelerate, and yet whatever force the baby applied, no matter how little, no matter how small the force is, the force was never a zero force. So there's a big question mark here. What is wrong? I'm going to be coming back to this, but let's quickly talk about the law better. So from the Newton's second law of motion, we can see that it says that if a force acts on a body, this body moves in such a way that the time rate of change in momentum of the body. So we are going to be taking note of momentum here. Momentum is mathematically expressed as product of mass and velocity. That is what momentum is. This is momentum. But from this statement, see that if a force acts on the body will move in such a manner that change in momentum with respect to time is equal to the force that was applied. So let's see what this is like. So if there's going to be a change in momentum, the change in momentum is not because of the mass, but because of the change in velocity. So that means that we have this. This is what the expression is saying. That is, there is a final velocity and there is an initial velocity with respect to time which is equal to the force. Don't forget, the body that was acted upon by this force is the one that has mass m. Then it moves in such a manner that the change in momentum with respect to time is equal to the force. So from this expression, we will remember from our from the Newton's from the equations of motion, equation of uniformly accelerated motion, we will recall that, if you will recall that final velocity equals initial velocity plus at. Then from this place, if we express a in terms of the other parameters, we'll see that a is equal to final velocity minus initial velocity over time. So here, that means that I can substitute a here. So I will have ma equals to f. Now this is what Newton's second law of motion says. And this, the time rate of change in momentum of a body that is acted upon by a force is equal to the force. So what is now the problem? If this is a law, that means that it must have been proven. That means that it must have been established. A lot of scholars must have, affirmed this statement. Yeah, it is right. A lot of scholars must have affirmed it, and even the law, there's nothing wrong with the law. But what is wrong is our perception about the law. This force, we don't regard it as what it's supposed to be. Now, there's something that I like to call domain of force. Now, in the real world, in the domain of force, we have so many forces there. And in fact, there are some of these forces that occurs naturally, whether we like it or not. One of them is the force of gravity. Whether we like it or not, there's a force of gravity that is acting at some level above the surface of Earth. Another one is force of friction. There is magnetic force, there's electric force, so on like that. There's drag force. Now, these forces, like I said, they occur naturally. So anytime you tend to apply a particular force on an object, and then the object does not move, or the object does not move in such a manner that you had intended. That is, the force, for instance, if you have a force of 50 Newton and you have a force of 50 Newton and a mass of 10 kg, that implies that acceleration is meant to be what? Acceleration is meant to be 5 meters per second squared. So whenever it happens that you apply a force of 50 Newton on a mass of 10 kilogram and you're not getting 5 meter per second squared as your acceleration, it's possible that you get lesser. In fact, that's what happened in most cases. It's possible that one of the cases you can have that A equals 0, you can have that A is less than 5, and you can even have that A is greater than 5. That's the thing. So it is not every time that I apply a force. Let me give you scenario why this acceleration can be 0. If you apply a 50 Newton force on an object whose mass is 10 kg, then the acceleration will be 0 if there is a counter force of exactly 50 Newton as well. So if there's a counter force of exactly 50 Newton, the acceleration is going to be equal to 0. Now, frictional force belongs to the domain of force. Like the domain of force I discussed earlier, frictional force is the one that will be responsible for this. There's something known as static frictional force. It is known as the force that you must meet up with before you can make an object that is at rest to start moving at all. So if you are applying force, and you have not been able to equal this force, you won't be able to cause an object to start moving in the first place. So which means that it's possible that this 50 Newton is not enough to overcome the frictional force between this object and the surface that it's resting on. So therefore, moving an object over a surface becomes difficult because of friction. Now, did you invite friction? No, you have not invited friction. In fact, you wish that it was not there. And it wasn't as if an external body decided to apply this frictional force. It is the result of your own action applying this 50 Newton force that causes frictional force to surface. So you cannot do without it, except you find yourself with perfectly smooth surface, which in the real world is not really possible. You can only see that in an ideal world. Anyways, let me not dwell much on that. So, which means that the body will not move and acceleration will be equal to 0. So, now, the second case, acceleration is less than 5. Yeah, the surface might have offered a friction, but let's say fortunately you have applied a force which is actually greater than the frictional force, the static frictional force, like I've explained earlier. So if you apply a force that is in such a way that it is greater than the frictional force, that implies that acceleration will occur, but at the same time, the frictional force would have removed its own portion of the acceleration, which means that it will no longer be up to 5 meters per second squared. Now that's one case. Another case is that if A can be greater than 5. Yes, A can be greater than 5. Now, in this case, now we will not be considering friction on the surface here. Let us consider an object that you want to throw in the air. Now, there is wind direction. The wind is blowing from here and there. So if you throw an object in the direction that the wind is blowing, what do you think will happen? The wind is going to make the object accelerate more, especially if the object is a light object. That is, the wind can affect it. So if you throw that object with a certain force, now you expect a 5 meter per second acceleration, meter per second square acceleration. But because of the direction of the wind, because the way the wind is blowing, it increases the acceleration. So look at this. So which means that it is not always true that F equals to ma. Now, from this whole thing now, we are getting to see that indeed, if F is really equals to ma, then what is now wrong with the law? Mind you, there's nothing wrong with Newton's second law of motion. Like I said earlier, it is the way that you have been perceiving it that is wrong, which is what I intend to change in this video. Now, let us see a better way to put Newton's second law of motion actually is that in this domain of force that I described earlier, as I said, there are so many forces that want to act: frictional force, tension, and the likes. So whenever you apply a force on an object and there is the influence of an external force, then you no longer talk about force, just mere force. Then you talk about a different type of force entirely. Not type of force, but then one of the forces that belongs to the domain of forces. So that's what we'll be talking about here. Now, so which implies that Newton's second law of motion is not really talking about a force that you have applied. It's talking about a particular force, which is a result of so many forces together. That is, whatever action that is happening, whatever action that you intend to happen on a mass that you're applying a force on, provided that there are external forces that have acted on this object, even the ones that you cannot do without. So I'm not even trying to say external force like somebody intentionally applied an external force on the body after you have applied your force. No, I'm talking about the external forces that the application of your own force is going to bring about. Friction is going to be relatable to many of you. So whenever you apply this force, especially when you want to move it on the surface, there is frictional force. So, which implies that, and if you read further on Wikipedia starts to describe this force, and you'll be able to see that, oh, so what Wikipedia was actually saying in the first place is not exactly the force that acted on the mass. It is actually called a net force. So the force that is equal to MA is not just any force. It is what? It is a net force. So, which means that Wikipedia should have stated earlier that whenever a body is acted upon by a net force, it moves in such a manner that the time rate of change in momentum of the body is equal to this net force. Then that will be 100%. Because what is net force? Net force does not even care how many forces. Net force does not care and what force have I not invited. Net force is just particular about the fact that, okay, all of you want to act together, let me represent you all. That is what net force is. Okay, force A, force B, force C, force D, up to force Z. All of you want to act together. I don't have any problem with that. All I want to do is represent all of you. So this net force represents every force that is acting in the system, both in magnitude and in direction as well. So that is what net force is. And that is what is always responsible for acceleration. So if you remember the other time, I said that every force, every non-zero force should produce an acceleration, provided the mass is never going to be equal to 0. So which means that the baby that is trying to push an object, or pull an object to himself or herself, and the object is not responding, it's not because the object is too heavy, but because there is a force that is counteracting the action of that baby. So which implies that in that situation, let's assume that it is frictional force, then there is the applied force by the baby, F from the baby, minus frictional force. Now this is equal to 0 because acceleration did not occur. So which implies that the F that the baby is applying is equal to the frictional force that the surface that the object is on is given. So that is why the object did not move. Don't forget, the baby applied a non-zero force, but there's nothing that stopped net force from being 0. Net force can be 0. It might be that when everything acts all together, it's just like, let me give you a scenario. Let's say somebody is contributing money to buy a particular thing. Now let's say the thing will cost 20x. Now this x is the currency that I'm spending in this video. So 20x is what this object will cost. So the person has contributed up to 20x. But upon getting to where the person is making this contribution, let's say in a bank, the person realized that the bank have already removed a charge of 20x. Now, the problem is not because the person has not contributed up to 20x. The problem is that there is an action that counters what the person has done, which gives the person 0 effect. So which means that the person will not be able to buy whatever they intended to buy. So that's exactly what is happening with net force. Okay, we don't care what you have done at the end of the day. All we care is that were you able to give the desired result. So that is what net force is about. So the reason why you would have a zero acceleration is not because of a non-zero force. Actually, it's because of a zero. It's not because of a zero force. So if you have applied a force that is non-zero, you can still have zero acceleration. How? Because the net force might be zero. So this is exactly what we are talking about in this situation. Now, about net force, which also I call resultant force, I have made a video about it. In fact, I've made two videos, section A and section B. I would like you to see these videos. It gives proper insight as to what net force is. In different cases, how do we calculate net force? In different scenarios, how do I get the net force? So that I can always be accurate as to what the action is, as to what the acceleration is going to be. I'm going to be putting the link to the video in the description below. So please check it out and have a better understanding about what net force is, because in this video is just to open your mind, it's just to make you have an insight as to what Newton's second law of motion states. So please also try and subscribe to my channel, because I'll be posting videos like these, interesting videos about physics, interesting videos about mathematics. I'll start series of lectures, motion, machine, and the likes. So I would like you to be the first person to view all these videos whenever they come up. So please subscribe. Thank you very much. I'm Isaac, but I'm not Newton. Thank you.